session, I'll talk about something which is very familiar to us, and in fact, this probably is the most familiar stuff that we use every day. That's water. And this is so common, and in our lifetime, we have seen water all around us, and we have almost taken this for granted. So the question I think will arise, why did I pick this topic to speak? I think by the end of this talk, I'll be able to convince you that this is something worth discussing, worth comprehending, and this is really an important issue. So we know H2O. This is the water molecule. It has 2 hydrogen atoms and 1 oxygen. This is known to all. To make the story interesting, I will go a bit behind what is happening here. Hydrogen is the most abundant atom in the universe, but the first hydrogen atom, it didn't appear right after the Big Bang. As you know, that was the start of this universe. It took some time. It took around almost 400,000 years after the Big Bang. We have the first hydrogen. It was because at the start, at the very beginning, the universe was much smaller, very dense, and the temperature, it was very high, and the temperature was so high that neutral atom, there was no possibility for it to form. You know, hydrogen atom, if we talk about hydrogen atom, it has 1 proton at the center, the nucleus, and it has 1 orbiting electron. But this electron, it is bound by the Coulomb force, and this binding energy is such that if the temperature is very high, the electron can no longer stay with the hydrogen proton, so it becomes ionized hydrogen. When the temperature becomes lower, there is a possibility of forming neutral hydrogen atom. So the universe had to wait 400,000 years approximately before the neutral hydrogen atom was formed. The story of oxygen is completely different. To form water molecule, you need oxygen, and oxygen came up much after the Big Bang. The history goes back almost a few billion years back, and oxygen, it was actually formed inside the stars by nuclear fission. And this thermonuclear fission, it needs a long time to run, and as a result, we had oxygen after several billion years, the Big Bang singularity. So, you know, the first oxygen atom, it was formed, as I said, around a billion years of the Big Bang, after the Big Bang. And if you look at the cosmic history, then you will see that it started here, and somewhere around this place, there is this matter radiation decoupling, and at that decoupling, there was that possibility of neutral hydrogen formation. And after that, the stars were formed. Inside the stars, you have that nuclear fusion, and as a result of different chains, fusion reactions, we have our oxygen. Still, the universe is quite hot. Eventually, when the temperature becomes suitable, we have oxygen and hydrogen in its atomic form, and they combine and form water molecule. And then something very interesting happened, and that will be the main theme of our story today. Now the question is, as I asked at the beginning, why bother? Water is everywhere, and we see it every day, we use it every day, and unfortunately it's also a very much truth of life, we waste it every day. So why bother about water? Particularly in this part of the world, we have seen water all around us all year through. But as I said at the end of this talk, I hope I will be able to convince you this is a very important issue, and we need to look at water in a different view. So water, as we know, it can be found in many different forms. For example, we have all seen the water vapor when we have a cup of tea or coffee. We have seen the water droplets, the liquid water, and in many parts of the world there is snow, and we have seen the snowflakes, the beautiful snowflakes that nature makes. This is the snowflake. You can see it here, hexagonal and such artistic pattern created by the nature itself. So the difference is in the energy. When the water molecule has high energy, it is vapor. When the energy is a bit lower, it is liquid. And if the energy is lowered further, the ice crystals form, that is in the solid form. And this is very common example of phase transition. This is the gaseous phase, liquid phase, and solid phase. For us, as a biological entity, the liquid phase is very important. Now we'll talk about the water molecule, and this is the most important bit of this talk. You know, from the chemical formula you can see it very clearly. We have H2O, so 2 hydrogen atoms and 1 oxygen. They are forming chemical bond, and at the end we are getting the water molecule. The bond formation, I will not make it any more complicated than it needs to be. I will try to put it as simply as I can. This bond formation is covalent in nature. Hydrogen has 1 electron and oxygen has 6 electrons in the p orbital. It wants to form a stable structure, so it requires 2 electrons, and hydrogen, as it has 1 electron, if it has an opportunity, it will try to get another electron to its orbital. So what happens? 2 hydrogens, they share 2 electrons with oxygen, and oxygen, they share 2 electrons with hydrogen. In this way, the hydrogen kind of feels I have 2 electrons that I need for stability, and the oxygen feels I have taken 2 electrons from hydrogen, which is actually shared, so I am also getting stability. And as a result, we have covalent bonding and water molecule is formed. But the important thing is, there is that term in chemistry which we call electronegativity, which is very important. When an element takes up electron, it has a certain capability of taking up that electron. Some elements are more inclined to take up electrons than the other elements. What happens for hydrogen and oxygen is oxygen is more electronegative than the hydrogen. As a result, the electron sharing is not equal. They are sharing their electrons, but oxygen is taking up more of the shared electrons compared to the hydrogen. As a result, if you look very carefully in the microscopic domain, you will see the oxygen, since it is taking electrons more than its fair share, is slightly negative. And since the hydrogen is giving up its electron a bit more to the oxygen, it is slightly locally positive. As a result, we have something wonderful which we call the dipole moment, and this is also depending on the bond angle, because you see this is plus here close to the hydrogen, minus close to the oxygen. So there is a dipole moment running from the negative charge to the positive charge in this direction and also in that direction. And if you do a little bit of vector analysis, you will see that dipole moment does not cancel each other. These moments cannot cancel each other because they are not along the same line. There is an angle, so if you resolve it into components, you will see there is a dipole moment which is running from the positive charge to the negative one, negative charge to the positive one, and this is the dipole moment. And this is extremely important, and everything I will say from now on will depend on this dipole moment. Because of this dipole moment, when temperature is lower, we can have solid water, which is ice. And if you look carefully, we will always see the red part, which is oxygen, which is slightly negatively charged compared to the hydrogen. The blue part is the hydrogen. When you are forming solid, the red part is always connected to the blue one because they have opposite charge. And this opposite charge leading to the dipolar interaction, that gives the structure of water in the ice form and also in the liquid form. In the liquid, the order is random, but for the solid you can see very clear hexagonal structure. And this structure gives rise to the wonderful architecture of the snowflakes and all those things. So, due to this dipolar interaction, the structure is formed, and the kind of bond we are forming here, this is dipolar in nature, but it has another name. This is hydrogen bond. This hydrogen bond for water is quite unusual, strong, and we'll see that this hydrogen bond has led to so many amazing and strange properties of water. So, as I say, the hydrogen bond is responsible for the miraculous properties of water, and this is related to its structure. As a consequence, I will just focus on a few amazing properties of water, but there are many more, but due to time constraint, I cannot go on. The first thing is anomalous expansion. This is a common knowledge. If we heat something, it gets expanded. And this also happens for water. But there is an anomaly, and which is so important for the biological structure and for the marine life that it must be said. You know, when we heat something, it gets expanded, and as a result, the density goes down. But for water, the maximum density we see is around 4 degrees Celsius, and if you go further, the density does not go up, but it goes down. And as a consequence, we can see that in the countries around the globe where the temperature goes quite below the freezing temperature, in the lakes, in the seas, in any water body, we can see the upper layer is covered with snow, but we have liquid water beneath it. And that sustains the marine life. This only happens because when ice is formed, this is solid, but in terms of density, it is lower than the water below. So ice does not go down, it floats. And since it floats, the marine life has water beneath the ice sheet. And this is one consequence of that hydrogen bond and structure of the water. This is amazing. The second thing, this is another amazing feature. If you look at the physics of evaporation, when you put heat, the liquid gets evaporated. And there is a very clear connection, usually it happens in many liquids. It depends, the evaporation temperature depends on the molecular mass. If you follow the common trend of molecular mass versus evaporation temperature curve, then water should become gaseous at much higher temperature, much higher temperature. So what would happen if water was a normal liquid? The temperature we have now, much lower temperature, I think. I'll get back to that. What will happen if water behaved like a common liquid? At that situation, the current temperature that we are experiencing now, there would have been no liquid water. All of it should have been evaporated. So water should be here, but in the gaseous form, if it was a conventional liquid. So what is happening here, due to this unconventional nature of water, we are having so much water in the liquid form. If it was a conventional liquid like many other, we almost have no liquid water in the earth. So that will be disaster for the biological entity. It has very high heat capacity. Again, this is a consequence of that amazing hydrogen bond. Heat capacity is the heat content that you need to change the temperature of a substance. Every substance has their own heat capacity, but the heat capacity of water compared to other liquid is unusually high. And what happens because of this? We have the thermal regulation around us. If water was like other common liquid, nights would get so cold and the day would become so hot that it would be completely unbearable for creatures like us. Since water can hold a lot of heat for a very long period of time without small change in temperature, water actually acts as the air conditioner for this earth. It keeps the temperature balance. If it was any other liquid covering the 70% of our surface area, then the temperature difference would be unbearable. So water is the compound which made this earth habitable. This point is also very important. This is one of the best solvents, and for every biological activity you need very efficient solvent, because you know that students of chemistry, if you cannot solve the reactants uniformly, the rate of reaction will go down and it will not work. Water is very good solvent because it is polar liquid. That dipole moment is actually responsible for its polar nature. It has a very high surface tension. Compared to other liquid, the surface tension is very high, and it also has very grave consequence on the biological system, because you know about capillarity. If you dip a tube in the water, you will see that water is rising inside the tube. This is capillarity. The veins we have, the water circulation in the leaves of plants, in all those aspects there is this effect of capillarity. And this capillary effect is stronger for liquids where the surface tension is high. As I said, the highly polar nature of water, it does wonders. Here is an example. If you look at the common solvents, you will see the dielectric constant, which is a measure of polarity. It is for water, it is 80. And you can see all other organic or inorganic solvents, the dielectric constant is so much lower. And it is very important. I will just point to one particular area why this is very important. This is the Coulomb law. We all know about the Coulomb law. The force between two charges is proportional to the product of the charges, and this is inversely proportional to the distance between the charges. The constant you see in front, it has a term epsilon naught, which is known as the permittivity of free space. This determines how strong the force will be. In case of water, we have mu naught here. In case of water, the mu naught will be replaced by mu, that is water's property, dielectric constant, and which is 80. For free space, if you take it as 1, for water it will become 80. And what will be the consequence? The consequence is very simple. The consequence is this: the Coulomb force becomes weakened in water 80 times weaker. So if I put two charges like this, the force I measure between the two charges, and then if we put the same two charges in water, the force between the two charges will be 80 times weaker. So what is its consequence? The consequence is wonderful. In human body and in biological entity, the current we have, it is actually ionic in nature. So we have sodium chloride, for example. We have sodium channel, calcium channel, potassium channel. All those ions are in our body and they are conducting electricity. So to conduct electricity, you need ions. Actually, we don't have ions, we have salts. When we put an ionic salt in water, since the Coulomb interaction is 80 times weakened, it becomes ionized. And that ion is doing everything. The talk I am presenting here, my neural activity, everything is controlled by those ions. If the dielectric constant of water was higher, then the ions wouldn't have formed. And unless those ions are there, we cannot really function. And I think many of you know that salt balance in our body is extremely important, the sodium level particularly. So this salt balance is actually for the ionic interaction within the body. These are just some examples. What I am saying is actually based on hard research. This is from Nature, and this talks about anomalous properties of water. This is chemical review, and it calls water the most anomalous liquid. So all the points I am trying to make, it is a matter of research. And then this is actually the last one. As I have shown you, and I started with the question, why bother? We should learn, we should know, we should realize that this is an issue to be bothered with. Everyday liquid water with its extremely simple form is actually quote unquote a miracle of nature. Because of its anomalous and strange properties, it controls so much, and we need to look at water with respect. We need to preserve it. We need to preserve your purity, because this liquid which is all around us is truly a miracle of nature, and it has so many anomalous and strange properties. It needs to be cherished. We need to respect this wonderful form of liquid, because not only we cannot exist without it, the environmental issues, sustainable development, the change in the weather pattern, everything is related to water. And water in this part of the world, as I said, this is abundant. But in many parts of the world, scarcity of water is one of the main problems. So water management, not wasting this asset, is very, very important. This is closely linked with our survival. So I picked this topic because I wanted to share that something we see every day, something we use without a care, actually needs to be cared. This is the main message I wanted to convey. This is truly an amazing gift from the nature, this water. We need to look at it at a different level, preserve it, manage it. Thank you very much.